Hello. Welcome to Rates of Change, aka the Applied Differential Calculus. This lesson is all about applying what we have already done, work with the gradient function. It's finally putting that crazy dy dx into a practical application to see what it means and why we care about it. To start off, copy down your essential question, pause and rewind if you need to, but today we are going to determine how rate of change is related to the gradient function. So remember what we've said about the gradient function, f prime of x. That's all this is. Gradient function is just f prime of x. It's a measure of how f of x changes as x increases. Now, we have already said that this is essentially the slope, or otherwise known as the gradient definition. But another way to say this is that f prime of x measures the rate of change with respect to x. And this respect to x nomenclature here, this is really just a fancy way of saying x will be in your answer somewhere. So don't be too intimidated by that language. So what does all this mean? Why do we care? Well, for starters, this is really useful when we are working on problems that involve time. So this is really important. If you are measuring how a variable changes when time is passing, then you are applying mathematics to a situation that is dynamic. And this is where we really start to see applied mathematics like what you see in physics or in financial applications. But what it really simply means is the situation is moving. And is it just me, or does anybody else really feel like Mr. Boucher missed an opportunity for a sweet situation meme here? Or is Jersey Shore not a thing anymore? Anyway, let's look at a few examples in which we explain the gradient function as a rate of change. Okay, example explanation number 1. If c represents the value of a car on a day-to-day basis, we can say that c is a function of time, where c equals f of t. That means the gradient function dc over dt, or f prime of t, represents the rate at which the value of the car is changing. So what does that mean? Well, maybe you have a really nice collector car, like a powder blue 57 Chevy Bel Air. That thing is increasing in value as time goes on. But if you drive a normal car, like a 97 Chevy Cavalier, sorry, that thing is just going to get harder and harder to sell. It's losing value as time passes. So that's what the gradient function tells you. It's how quickly is your car gaining or losing value at any given time. Okay? So when we talk about the rate at which this value is changing, we can say that it's the rate at which the value is increasing, or maybe it's something known as like the inflation rate. Or if it's losing value, like most of our cars will do, then we might call that how much the value is decreasing, or we would call that the deflation rate. Okay, example explanation number 2. If s represents the distance measured from a fixed point to a moving object, then s is a function of time. S equals g of t. Thus, the gradient function ds over dt, or g prime of t, measures the rate of change of this distance. Now, maybe this object is a goal, and a soccer ball is moving toward it. Well, the rate of change of that soccer ball obviously is just how fast is that ball moving toward the goal. And you know this rate of change as velocity. Hence, if a function gives us the position of an object, then differentiation gives us its velocity. Hooray for physics! Okay, so problem number 1. This is a very much applied rates of change differentiation problem, something you would see in a very basic physics question, or this would be something on your external assessment. So this is a good one to take a look at first. The volume of water in a container is given in centimeters cubed and is given by the formula V equals 300 plus 2t minus t squared, where t is the time measured in seconds. So we have an equation for volume that is changing with respect to t, time. Okay, so what does dV over dt represent? Well, we know that dV over dt is the rate of change of that the variable in question, which is volume in this case. So we would say it's the rate of change of volume of water in the container. Now that's still kind of obtuse language. I'm not crazy about it. Let's think about this for a second, what it means. Well, if the volume of water is changing, that means it could be increasing or decreasing. The rate of which it's increasing or decreasing just talks about, hey, how fast is that happening? So this tells us how fast water enters or leaves the container. So what units are used to describe this dV over dt? Well, we're talking about volume still, right? We're talking about the rate of change of volume, so that's still going to be in those units, centimeters cubed, but this is happening in terms of time. Well, it must be changing with respect to time. Our measurement of time was in seconds here, so it's centimeters cubed over s. This is the American way that we would write it out, most standard. However, we know that the IB folk can be a little hoity-toity and fancy sometimes, and they like to use negative exponents instead of fraction bars. So this is the IB way of writing it. But the English way of saying this is very simple, right? It's going to be gaining a volume, centimeters cubed, per second. That's how we describe velocity or rate of change. It's something that's happening per unit of time. So now we need to find the value of dV dt when t equals 3. Okay, so this is just the exact same kind of thing that you've seen on your homework problems before. The first thing that we need to do is find what is dV over dt. Well, that's a very simple differentiation here. We know that 300, that goes away when we are doing our differentiation. 2t, that changes to 2. Negative t squared changes to negative 2t. So then we can plug in t equals 3 into our gradient function, 2 minus 2t. 2 minus 2 times 3, we have 2 minus 6, and that gives us negative 4. Boom, done. Exact same problems that you guys have seen on your homework. Well, what does this answer tell us? This is where we get into new stuff. Apply it. Okay? Well, we are talking about at a specific moment in time. So at 3 seconds, dV dt equals negative 4. Well, again, what units did we just say this is going to be in? Centimeters cubed per second. So the volume is changing negative 4 centimeters cubed per second. What that means is at 3 seconds, the container is losing water at 4 centimeters cubed per second. Well, how do you know it's losing? Well, my rate of change was negative. That means that the volume is decreasing with respect to time. So that answers part E. Why is the answer to C a negative value? Because the volume of water is decreasing. Alright, you guys, so that does it for me for this lesson. We've just talked about rates of change and how they are related to the gradient function. Rate of change is just the practical application of the gradient function in real-world scenarios. Extremely useful tool. Hopefully you guys use it in your examples and homework assignment coming up. Have a wonderful day.